Hey, good morning. Um, just one administrative announcement this morning. The Examity practice exam is live now, so make sure that you go on, take a look at that. At that exam, I did post announcement last week about it, so there's more detail in there. But basically, the idea is that this Examity practice exam, it doesn't count for anything in your course grade. It's really only meant for you to be able to log on to Examity, get the account set up, and go through the process of starting an exam, starting the Examity session, going over to WebAssign, having the Examity browser add-on put in the password for the exam, start the exam up, take it, and then, close everything out at the end. So the Examity practice exam only has like a handful, I think maybe 5 dummy questions in it. It's timed to 15 minutes, but it's not really meant for you to go in and work the problems and really get a good score. It's more meant for you to be able to make sure that you get into the exam, make sure that you've gone through the process once already before an actual exam, and also to make sure that all the tech works. So I would recommend that when you do this, um, use the same computer, the same setup, and all of that you plan to use for the actual exams in the future. So that is the goal of the Examity practice exam. Again, more details on the Blackboard announcement that should have been sent to your emails, but if you didn't see the email, it's also up on Blackboard in the announcements tab. So the quote of the day today is actually kind of it, it- it's a it's a question that somebody asked in a Facebook group that I'm in. Um, And when I first read it, I thought it was kind of a dumb question. And then I thought about it and I thought, well, there's actually, I think, a deeper meaning to this. So I figured I would make it the quote of the day for the first couple of days this week. And the question was, if you could teleport into the future and teach your older self anything, what would it be? So it's kind of a play on the trope, if you could teleport into the past and tell your younger self anything, what would it be? And people always either say the Powerball number or something like that, or they, say whatever they think their most important piece of wisdom is, or, don't do this thing or do that thing instead or whatever. Um, but I really like this because, that we naturally think, well, information flows forward in time. So what could my younger self teach my older self? Seemingly nothing, right? Because my older self has all the experiences of my younger self and even more. Um, but I think really what it was getting at is there's a lot of wisdom in youth that we maybe lose as we get older and as we, have some negative life experiences. They might warp our view of the world. So it's valuable every once in a while to think back, um, to how we thought when we were, 10 years younger, 5 years younger, something like that, maybe even 15 years younger. Um, what life lessons did we somehow inherently know back then that we may have lost over time? So I think it was kind of an interesting question. A lot of people were like tearing him apart in the comments, like, this is a dumb question. This doesn't make any sense. Um, but I think it's more interesting than it appears to be at first. Okay, so the plan for today is to finish section 5.4 on dividing polynomials. So unfortunately, I was feeling under the weather last Thursday, so we canceled class. We're picking up today with dividing polynomials in 5.4. Let me just check the course schedule here really quickly. I scroll back to where I was. So we're running a little bit behind. We have Unit 2 exam coming up at the end of the month, the week of the 28th. So we um, just really quickly, we have a couple weeks before that Unit 2 exam, but I do recommend doing the Examity practice exam this week or at the latest early next week, just in case there are any tech issues. It's always better to get those sorted out well ahead of exam week. So exam week for the Unit 2 exam is coming up on the 28th. And we'll likely adjust the material that's slated for that exam in light of where we're at in the course as we get closer to that. Um, okay, but today's plan is to finish up dividing polynomials and to start into chapter 6. So starting in the chapter 6, factoring, kind of like a lot of Math 108, this is going to be somewhat a review of Math 90 or of elementary algebra or Algebra 1 if you took it in high school. Um, so when we move into factoring, we're going to go a little more quickly. We're going to treat it, a little more as a review. But I do understand that this is challenging material. This is in Math 90. This is kind of the like over the hump material. This is the material that it's usually the first material that's really challenging for students. Um, so seeing it a second time is definitely helpful. So we're going to go through it about at the pace of a review, but maybe a little more slowly because it is the more challenging material from, or some of the more challenging material from Math 90 from the prerequisite course. But that being said, we're going to cover it at a quicker pace than we would if it was a first introduction to the material. So so we will go through chapter 6 a little more quickly than you might have gone through that material in a previous course. But if we're going through it quickly and you have any questions on anything, definitely feel free to ask. I'm happy to slow down and answer any questions that you'd have. All right. So moving into dividing polynomials, we looked last time at dividing monomials or binomials or polynomials by a monomial. So something like something like this, where we said the strategy was to take advantage of this just general fractions property. This isn't really even an algebra property so much as an arithmetic property, just the way fractions work, that I can take a sum over one denominator and break it into two fractions with that common denominator. And then I can simplify the monomial over monomial. I can divide out a factor of x in the first one and divide out a factor of x in the second one as well. Now, if we're dividing by a binomial, that's fundamentally different. If we're dividing by a monomial, the numerator can be a monomial, a binomial, a polynomial. That all pretty much works the same as I just showed. But when we switch the denominator from having one term from having one term to two terms, we have something fundamentally different now. What's really the reason for the difference? Well, it's because we have a division bar. So our overall operation is on the multiplication division level of PEMDAS, the order of operations. But then in the denominator, we have a subtraction. So we have kind of a division mixing with a subtraction. Those are two different levels of order of operations. They're not going to work as nicely. Or if I have a monomial where I have maybe a number multiplied by a variable, I kind of have division mixing with multiplication. Well, multiplication and division are the same level of order of operations. They work a little more nicely together. So we can't do something like, make this 3x squared over x minus 3 minus 10x over x minus 3 and so on and really get anywhere meaningful doing that. We need to take a completely different approach. Now, if I look at this, kind of philosophically speaking, I have a quadratic in the numerator and a linear in the denominator. It kind of feels similar to this, right? I have like a quadratic in the numerator, linear in the denominator. I ended up with a linear because power 2 minus power 1 gives me power 1. I kind of expect to have a linear come out of here. And in fact, I know that, this could be maybe something like just say x minus 1. I'm just not saying this is what it's equal to, but I'm just saying pretend. Well, if numerator over denominator equals x minus 1, that would mean that x minus 1 times x minus 3 would be the numerator. And we see that that is like a plausible thing, right? If I have the product of two linears, of two binomials, that gives me a quadratic polynomial. That kind of feels right. So I'm looking to get a linear function out of here. Now the question is, how do I actually go about that? And the answer is I basically use long division. And you can think back to long division analogies and so on for just arithmetic, for just number divided by number, and things like, whatever, large bags of candy of say size 100 each and smaller bags of size 10 each, and individual units of candy, and splitting them up between trick-or-treater bags or something like that. Or there's lots of different analogies. But basically we're going to start by saying, okay, I have x minus 3. In some sense, x minus 3 goes into my leading term, 3x squared, how many times? Or what I kind of mean, phrasing that differently, is x minus 3 times what gives me a term that looks like 3x squared. Well, I need to multiply that by 3x, so that 3x times x gives me 3x squared. But then I have this other piece here, 3x times negative 3 is negative 9x. And all of this gets subtracted. So if you're a little weak on long division, that's okay. I would recommend going back and doing a few long division problems with just numbers to remind yourself how all the mechanics work and where everything comes from. We're just applying that same idea to polynomials here. You can even think of like x and x squared and so on, almost like powers of 10. So 3x squared minus 3x squared, those go away. And negative 10x minus a negative or plus a 9x gives me negative x. And then plus 30. And now I ask the same question. How many times does x go into negative x plus 30? Or in other words, x times what would give me something that looks like negative x minus 1. Minus 1 times x is negative x. Minus 1 times negative 3 is plus 3. And I'm subtracting this off. These bits go away. And I end up with 30 minus 3 is 27. Can I multiply x by anything to make a 27? I mean, I guess I could do like a 27 over x, but that's not going to work so nicely. So we're done here. So what can I say then? That this quotient I can say that this is 3x minus 1. Hey, that's that linear piece that we were expecting, plus the remainder divided by the original denominator. In this case, x minus 3 didn't divide nicely into the polynomial in the numerator, but that's okay. We have a remainder left over, but we were able to basically break out a linear part with a remainder. Importantly, in this remainder, the degree of the numerator is less than the degree of the denominator. If we had maybe mistakenly, say, stopped here and thought that this was the remainder, well, we see negative x plus 30 is a linear, it's a first degree polynomial, as is the denominator x minus 3. That means we can divide out some more. So we know that we're left with a true remainder whenever the degree of the remainder is less than the degree of the original denominator. Okay, and let's go through one more example of that. 2y cubed minus 4y minus 42 over y minus 3. Now here, as we're going along, we might do something like, how many times does y go into 2y cubed, 2y squared, and then I get 2y squared times -3 is minus 6y squared, and I want to subtract this. And I end up with a little bit of a kind of a challenge here because my terms aren't really lining up nicely as far as the degree goes. So if I look ahead a step or two, I see that this is going to be a bit of a problem. How do I resolve this problem? I go back all the way to where I started and I say, okay, I have in my numerator a cubic. Well, I want to account for all of the possible degrees. Just like how if I had 1043, I would write it as 1043, this 0 being a placeholder for the 0 hundredths. I want to just write 143. Similarly here, I want to give a placeholder for the quadratic term where the coefficient is just 0. So plus 0x squared, y squared, minus 4y minus 42. If I forgot to do that initially, I kind of pretty quickly end up in a situation where I'm a bit like twisted into a pretzel and things aren't quite working right. And that's probably a good reminder to, okay, go back and let's fix this, make it right from the beginning. And there's y minus 3. So we asked the same question, how many times does y, our leading coefficient, or our leading term in our denominator, go into 2y cubed? Or in other words, y times what gives me 2y cubed? That's 2y squared, just like before. 2y squared times y is 2y cubed. And then I have minus 6y squared. And now things are lining up a lot nicer. My 2y cubes go away, and I have minus a negative or plus 6y squared. I'll bring down my next term, minus 4y. How many times does y go into 6y squared? Or in other words, y times what gives me 6y squared? Well, that's going to be a plus 6y. 6y times y is 6y squared. 6y times -3 is negative 18y. Again, my 6y squareds go away. Minus a negative 18y is plus 18y. And then it gives me 14y. And I have one last term to bring down, minus 42. And once again, I ask, how many times does y go into 14y? Or in other words, y times what gives me 14y? Well, that must be a plus 14. 14 times y is 14y. And 14 times -3 is minus 42. And hey, everything cancels out. I'm left with a remainder of 0. So that's really nice. And I see that this quotient, 2y cubed minus 4y minus 42, all divided by y minus 3, just gives me 2y squared plus 6y plus 14 with no remainder. So I would have something like plus 0 over y minus 3, but we just don't write that. Okay, so that's a rundown of polynomial long division. Again, this is something that you've likely seen before in a couple different contexts, both in the arithmetic side of things, dividing numbers, and in the polynomial side of things, this is something that's typically covered in, Algebra 1, elementary algebra. So I did go through it, like I mentioned, a little more quickly than a first introduction. So if you need to dust off the cobwebs a little bit on this, I would recommend going back and just running through a couple of these problems by hand with maybe, a 3-digit number divided by a 2-digit number, do a couple of those problems just to kind of get the mechanics down. And then maybe drill a few of these problems, and I think it should come back pretty quickly. Okay, so that wraps up our discussion of operations on polynomials, and that actually wraps up the entirety of chapter 5. Are there any questions on anything up to this point in either today's class in chapter 5 and polynomials? I should say in operations on polynomials. We're still continuing with polynomials and factoring, but anything in chapter 5. Okay. So let's take a look then at chapter 6 at factoring, and let's look at the first idea in factoring, greatest common factor and factoring by grouping. So let's just start by finding the greatest common factor of three numbers, just to remind ourselves kind of how it works. So what is the great what is the greatest common factor? Well, remember, a factor of a number is an integer or a natural number that can multiply another integer or natural number to make the number we're interested in. So for instance, let's say 36, 3 would be a factor of 36 because 3 times 12 is 36, or 6 would be a factor of 36 because 6 can multiply by 6 to make 36. But 7 would not be, because we can't really multiply 7 by any natural number to get 36. So we could, if we wanted to, we could make a list of factors of 36. And the idea of the greatest common factor is there might be a factor that is common to two numbers or three numbers or even more than that many numbers. So the number 1 is going to be a common factor to all numbers. So we definitely have, 1 is a factor of 117, of 39, as well as 78. But is there a bigger one? Is there a number like 2 or 3 or 5 or something that is a larger number than 1 that is also a factor to every one of these three numbers? And that's what we're interested in knowing. How do we go about this? We start by getting a prime factorization for every number. This kind of breaks down on each of these numbers into its building blocks, so to speak, the prime number factors. And we look at something like 39, and we might just recognize right away that this is divisible by 3. I have a divisibility test for 3. It says that if the sum of the digits of the number is divisible by 3, then the number is divisible by 3. That's one of the, more famous divisibility tests that's non-trivial. If it's even, it's divisible by 2. If it ends in 5 or 0, it's divisible by 5. And if it ends in 0, it's divisible by 10. But probably the most famous of the ones that's not one of those, that's super easy, is divisibility by 3. And I see that 9 plus 3 is 12. 12 is divisible by 3. 12 is 4 times 3. So 39 is also divisible by 3. And I see that it is 3 times 13. If I do the same the same check on 117, 7 plus 1 plus 1 is 9. 9 is divisible by 3, so 117 is as well. I actually noticed that 117 is, well, it's almost 120, and 120 is 40 times 3. So this is going to be 3 times 39, or we just did 39. 39 is 13 times 3. And 78, 7 plus 8 is 15. 15 is 5 times 3. 15 is divisible by 3, so 78 is as well. So if I think of 78 over 3, 3 goes into 7 twice. 2 times 3 is 6. 7 minus 6 is 1. And 3 goes into 18 6 times. So I think 3 times 26 would give me 78. And I know that 26 breaks into 2 times 13. And so I've written these in columns. So I have like my first factor of 3, my first factor of 13. I have a second factor of 3 here, a factor of 2 there. I've written those in different columns. And then I look at my columns and I say, is there any column that is filled in by each of the 3 numbers? Well, this one and this one. So 3 times 13, or 39, is my greatest common factor. And I see that 39 is, of course, 39 times 1. I see that 117 is 39 times 3. And I see that 78 is 39 times 2. So these numbers all have 39 as a factor. So the greatest common factor of these would be 39. They all have 39 as a factor, so the greatest common factor is at least 39. And if I try to put anything else in, if I try to make the greatest common factor 39 times 2 or something, well, just the original 39 has nothing left to give, right? There's no more, there are no more factors in that middle number there. So this has to be the greatest common factor. So if I look at an example like this one here, I can take something like 3x squared y cubed and get something like a prime factorization for it. Well, the number is just going to factor to 3. And then I have my variables. I have 2 copies of x and 3 copies of y. These are all multiplied together. And 12xy to the 5th. Well, that's going to be 3 times 4, or 3 times 2 squared, times x, y to the 5th. If I see really what I was doing up here is I could think of this a little differently and come back up here and kind of edit this. I really see that this is like 3 to the first power and 2 to the first power and so on. I could even come all the way back to these 3's here. And instead of writing a 3 in a separate column, like a second 3, I could write 3 to the second power, 3 to the first, and 3 to the first. I have 13. Each of those is to the first power. And I have a times 2 to the first. I don't see any 2's in the 117 or the 39, so that's kind of like having 2 to the 0 power. So another way that I could think of building up my greatest common factor in a way that's completely equivalent to what we did, I write down each of my bases, 3, 13, and 2, that I found up here in the factorization of any of these. And then I raise it to the power that is the smallest power that I see. So I see a 1, and a 2. The smallest power I see is a 1. In other words, everybody has at least one factor of 3. Some have more than one factor of 3, but everybody has at least one. The smallest power I see on any of the 13s, they all have exactly the power of 1. So 13 to the 1. And the smallest power I see on any of the 2's, maybe I'll point to them with arrows. Well, I see a 2 to the first power, but I see a smaller power on some other ones. I see a 0 power. 2 to the 0 is 1. Then there's our 3 times 13. So I can take this method that I used previously, which was maybe a slower method where I broke everything out individually, combine things together in powers, and I see really what I'm doing is I'm taking each base to the smallest power that I see anywhere. So if I come down here, I have four bases, 3, 2, x, and y. I think of this as 2 to the 0 power, because 3x squared y cubed doesn't have really explicitly any factors of 2. It has 0 factors of 2. And these are 3 to the first power. So my greatest common factor is going to be 3 to the power what? Well, the smallest of any of the powers I see. Everybody has a first power, so that's going to be 3 to the first. What power should I put on my 2? The smallest of the powers I see up here, I see a power 2, but I see a power 0, so 2 to the 0 power. Now, what's really nice is for the variables, this idea works very nicely, right? X is just x to the first power. What's the smallest power I see anywhere on x? I see a second power, but I see a first power. Smallest power is 1. And on y, I see a fifth power and a third power. So y to the third. 3 to the first power is just 3. Let me say GCF equals 3 to the first power is 3. 2 to the 0 is just 1, so we'll omit that. And then we have x, y cubed. So for instance, 3x squared y cubed is 3xy cubed times what? Well, we're missing one of our powers of x here. We did capture the power of the 1 power of 3, as well as the 3 powers of y. So we just need to multiply by x. We need to multiply our GCF by x to recover 3x squared y cubed. Or for 12x y to the fifth, it's 3xy cubed times what? Well, we have our power of 3. We need 2 factors of 2. We don't have either of those 2 factors of 2 in our GCF, so we need a 2 squared, or a 4. We need 1 factor of x. We have 1 factor of x. We need 5 factors of y. We don't have 5 factors of y. We only have 3 of them. So we need 2 more factors of y as well. So if I multiply my GCF by 4y squared, I get 12xy to the fifth. Okay, so let's do a few problems related to factoring GCFs, greatest common factors. So here I have a few different polynomials, and I want to factor the greatest common factor out of each of the polynomials. So I have 5x and negative 15. Typically, I'm not going to involve the sign in finding the GCF, so I'll just leave that as a positive 15. And I know 5x is just 5 times x. Doesn't break down any simpler than that, because 5 is a prime number. And 15 is 5 times 3. I pretty clearly see my GCF is just going to be 5. So what does this mean? Well, what this means is that I can write 5x as, well, 5 times x, and I can write the 15 as 5 times 3. I remember my distributive property. It says a times b plus c, or b minus c, equals a times b plus a times c, or ab minus ac. Quite often I'm going left to right. Quite often I'm distributing. But I can kind of like undistribute, right? If I see that I have the same factor in all of the terms, I can factor that out. I can undistribute that factor. I can take this 5 that's a factor in each of my 2 terms and kind of pull it out front and I'm left with x minus 3. So I found my greatest common factor. I can rewrite each of my terms as that factor times some other stuff. And then I can factor that out. I can undistribute that factor and pull it out in front. I have something similar here. I noticed that when you get better at this, you kind of find the GCF a little more easily. I see that 20 is going to be a factor of both 40 and 60. And I don't think anything bigger is going to be, right? So 60 is 20 times 3, and 40 is 20 times 2. And then I also have my factors of x. I have 2 factors of x in the first term, 1 in the second term. I can put 1 factor of x as my greatest common factor, as part of my greatest common factor. I cannot put a second factor of x because the 40x does not have a second factor of x to match. So 20x times 3x and 20x times 2. And these are connected with a minus. Oh, how did I do that? Sometimes I love OneNote and sometimes it drives me up a wall. There we go. So I have 20x times 3x minus 20x times 2. I have the same kind of structure here. Now my a looks a little more complicated. It's 20x now instead of just a number. But the same idea applies. I can factor out a 20x times 3x minus 2. If I distribute, I can check 20x times 3x does give me 60x squared. And then minus 20x times 2 is minus 40x. Now, if I look at an example like this one, factor the greatest common factor out of 3x minus 1. Well, if I come over here, 3x is just 3 times x. 1 is just, I guess we can write its factorization as just 1. I see there's actually no greatest common factor here larger than 1. This type of polynomial we would call prime. It's a little bit like a prime number. So like how the number 3, its prime factorization is just itself. You can't really factor the number 3 into more simple factors the way that you could factor 6 as, say, like 2 times 3. So we say that 3 is a prime number because you can't break it apart this way. We say that a polynomial is a prime polynomial if it can't be factored into a simpler form. 3x minus 1 would be an example of a prime polynomial. There's no way to really factor this into the product of 2 polynomials or the product of a monomial and a polynomial. So since there's no way to break it down into factors of smaller polynomials, we call it a prime polynomial. And it just kind of stays as it is. So it just stays like that. Give me 1 second here. Okay, and then last example in this problem here is we could have a polynomial like this. We could have 3 times x plus 3 minus 2x times x plus 3. So here, the thing that we are seeing is common between both terms, the a, so to speak, that we're looking to factor out, is even a little bit more complicated. It's actually a whole binomial. But that's not really a problem, right? This is just like 3a minus 2x times a. And that a can factor out to a times 3 minus 2x. It doesn't matter if that a is just a variable like x or a number like 5, or if it's something more complicated like a binomial x plus 3, it can still factor out. So I can bring this x plus 3 out in front, factor it out, and I'm left with a 3 from the first term and a minus 2x from the second term. And one last example in this section. Building off of this idea, we can actually build up another layer, and we can say, well, if I can get my complicated polynomial to look like this, if I can get to this intermediate step where I have the same binomial factor in both terms, in two terms, then I can factor it out, and this looks like a pretty nicely factored form. So sometimes I can get to that step pretty easily. Sometimes I can get to this intermediate step pretty easily. If I look at an example like this one here, this is an example where I can get to that intermediate step pretty easily. Now, as kind of a general rule, factoring a cubic is quite difficult and well outside the scope of this course. But for some particular cases like this one, it's actually pretty straightforward. So if I look at my first two terms here, note that this first bit here would, if I distributed, give rise to two terms, 3x plus 9. If I look at these first two terms, 5x cubed plus 3x squared, if I ask just from those two terms, is there a common factor that can be factored out? Well, the 5 and the 3, those are both prime. They don't really work well together. But the x cubed and the x squared, I could factor out a factor of x squared. That would leave me with 5x to make 5x cubed plus 3. And then for my second two terms, let me lump the negative in with those. From the second two terms, negative 5x minus 3, what can I factor out here? Well, I guess there's not really a greatest common factor, but I can make these last two terms, negative 5x minus 3, look like this binomial by factoring out a minus 1. And now I see more clearly that I have a factor of 5x plus 3 in this first term and a factor of 5x plus 3 in this second term. I can factor that out. And what am I left with from the first term? X squared. From the second term, minus 1. Okay, so that wraps up 6.1. We're going to move into 6.2, factoring trinomials, and then a bit later on looking at special products. As a little bit of a side note, x squared minus 1 can actually be factored a little bit further. We might kind of recognize this from our previous work, where we looked at multiplying special products of polynomials. We might recognize that the difference of two squares resulted from multiplying something like, say, x plus 1 times x minus 1. So we might realize, maybe just by chance, maybe you just recognized it, or maybe you didn't see that that we could actually take, say, a quadratic like this and factor it this way. So that's kind of our goal in section 6.2, factoring trinomials, or really factoring quadratics, factoring things that look like x squared plus bx plus c, factoring things that look kind of like this, or that maybe have a cross term, that maybe have an x term in it. So our goal is to write x squared plus bx plus c as x plus m times x plus n, where usually we want m and n to be whole numbers. So let's just go through some examples. What is our goal here? If I multiply out x plus m times x plus n, I get x squared plus m plus nx plus m times n. And if I match that up to x squared plus bx plus c, I really see for m and n, I have two criteria. I'm looking for two numbers, m and n, that multiply to make c and that add to make b. If I find such an m and n, then I should be able to break this quadratic up this way. Importantly, these are only quadratics that have 1 as the leading coefficient, where the coefficient of x squared is the number 1. So for quadratics where the leading coefficient is not 1, if it's something more complicated, then we have to use a slightly different, slightly more general process. But for x squared plus 8x plus 15, I'm looking for two numbers, m and n, that multiply to positive 15 and that add to 8. And of course, this is going to be 5 and 3. So x squared plus 8x plus 15 is going to factor to x plus 5 times x plus 3. We can check that. The firsts give us x squared. The outers give us plus 3x. The inners give us plus 5x, so that's plus 8x. And the last give us 5 times 3, or 15. So again, I'm going a little more quickly through this than we would on a first pass, but I think this should be pretty familiar. So for a problem like this, x squared plus 11x plus 18, again, I'm looking for m and n, then multiply to make 18, and the add to make 11. Well, I know that I can make 18 by, say, 6 times 3, but 6 plus 3 doesn't make 11. I could also make 18 by doing 9 times 2, and hey, 9 plus 2 does make 11. So if I pick m and n to be 9 and 2, m times n, 9 times 2 is 18, and m plus n is 11. If I have the same cross term but a different constant term, I'm going to get a different factorization. So now I'm looking for two numbers that multiply to make 30 and that add to make 11. Lots of ways I could multiply two numbers to get 30, say 3 times 10, but 3 and 10, if I add those together, it gives me 13. But if I use 6 and 5, 6 times 5 is 30, 6 plus 5 is 11. Now, sometimes I have a problem like this, x squared plus 14x plus 48. Again, I want to find m and n, so that m times n is 48, and m plus n is 14. Sometimes I have a situation like this where 48 has an awful lot of factors. So I can actually come over here and go through my list of m's and n's. Well, I can always have a factor of 1. So I'll start with 1 for m. I'm requiring that m times n be 48. So n then has to be 48. And then I'll kind of check m plus n, 49. That's not 14. M could be 2. 2 is a factor of 48. 2 times 24, the sum is 26. That's also not 14. 3. 3 goes into 48. What is it? 3 times 16. But that sums to 19. That's not 14. I could do 4 times what? 12. That gives me 16, not 14. 5, well, 5 doesn't go into 48. 6 times 8, 6 eights are 48. And hey, 6 plus 8 is 14. That's exactly what we're looking for the sum. So 6 and 8 multiply together, you have 48, and added together, you have 14. So when I have a more complicated problem, I can come off to the side, write out my factors systematically, starting with, the smallest possible factor of 1 for one of them and working my way up and checking as I go along. So 48 just has a lot of different ways to factor it, and going through systematically helped us find the right one. So y squared plus 19y plus 60, again, I'm looking for two numbers, m and n, such that m times n is 60, and m plus n is 19. So I might think of some factors of 60. I might view this as a difficult problem and go over and start by doing 1 times 60, and then 1 plus 60 is 61. That's not 19, and go through the process. Or I might say, well, 6 times 10 is 60. 6 plus 10 is 16. Well, that 16 is pretty close to 19. Do I have another set of factors that's kind of close to 6 times 10? Well, I guess 5 times 12 would be 60, right? Kind of like the clock face. 12 groups of 5 is 60. And 12 plus 5, well, that's 17. So maybe I do want to come over here. Let's see, 1 and 60. That makes a sum of 61. That's not right. I'm looking for 19. 2 and 30, 32. 3 and 20, 23. 4 and 15. Well, hey, there we go. 4 and 15. So it wasn't quite 6 times 10 or 5 times 12. It was 4 times 15 is 60, and 4 plus 15 is 19. So that's the right way to go. 4 comma 15. So it's y plus 4 times y plus 15. So I think probably what most people would do is kind of a combination of the guess and check idea and the systematic idea. You kind of guess and check to see, okay, can I come up with the answer pretty quickly? If I try a couple of guesses in my head and it doesn't work out, maybe revert to the systematic idea. But maybe, maybe sometimes like the easier problems up here, I try a couple of guesses and I hit on the right one and I get the answer pretty quickly. If you always want to use a systematic method, I don't think that's a bad thing. You can do that, and you have one system that will always get the answer. But I would recommend, not relying completely on the guess and check method. So if you want to do guess and check, do a couple of guesses, and if you don't get it right, then revert to the systematic method. If you always want to use the systematic method, go with that. That's fine. But I wouldn't recommend relying completely on guess and check and never the systematic method. And I think we'll see why in a couple minutes here, maybe either today or next class. Here I'm looking for two numbers, m and n, that multiply to 18 and that add to -9. If I'm looking for two numbers that multiply to a positive number, those two numbers could both be positive or they could both be negative. If I want the sum to be negative, I can't add two positive numbers and get a negative sum, of course. So this has to be two negative numbers. So like -1 and -18 would multiply to make positive 18, but their sum is -19, not -9. So that's not the right combination. I could have 2 times 9, -2 times -9 gives me 18. Their sum is -11, so that's not quite right. I could have -3 and -6. That gives me a product of positive 18. And -3 plus -6 does give me -9. Looks like that's the right combination there. So I need x plus a -3 or x minus 3 times x plus a -6 or x minus 6. So our next one, x squared minus x minus 20, looking for an m and an n that multiplies to -20 and that adds to -1. So here I have an interesting situation where I have the product of m and n being negative. So one of them's got to be negative, one of them's got to be positive. When I go through systematically, I start with my m being the smaller number in magnitude and the n being larger in magnitude. I'm also looking for a sum that is negative. So if I have to pick one of these to be positive and the other negative, and I want the sum to be negative, I'm going to pick the larger in magnitude to be negative. 1 times -20 gives me -20. 1 plus -20 gives me -19. I'm looking for a -1. That's not right. I can probably make an educated guess here that 4 and -5 might be what I'm looking for because those are 1 unit apart. And 4 minus 5 is indeed -1. And so my factorization is x plus 4 times x minus 5. And that takes us to the end of our time today. So let me end the recording.